Yes, okay, students. After a rest, let's continue to today's class. Today's class, we will talk about serviceability limit state and what details that we need to care during the structure design, right? And previous we mentioned cover. Cover is the constructor values that we will use. And for the minimum cover, we need to consider the bound transfer, the transitions, right? Bound transitions. Bound force can be easily transferred from the concrete. Yeah, there are the three transmission of a bound stress, and another is the durability. For the cover, need to protect steel bars, and what else is the adequate fire resistance. And for fair resistance, that in columns design, that we need to really care these values. Yeah. Look at here for the columns. Here is use equidistance. Do not directly use the cover, but it's related to cover, right? And here, stirrups for the columns. This distance, AST, yeah, the axial distance should be checked. For UFI, that means design axial load under the fair condition and to the design resistance of the columns at normal temperature. If its column exposed on one side, more than one side, we should follow this chart. There is the standard fire resistance. Standard fire. If the columns should are 120, right, at this level, and the columns exposure more than one side, that means columns this side, and this side, what should follow this one. B is the minimum 8 bars. B means this one. B divide AST. Yes. Should near to these values. Right there. These values. Yeah, for the shear wall. Shear wall is another type of the support the beam in the shear wall. We not mentioned in the frame structure, but it's also a important structure members. For the shear wall, the wall thickness, just like the covers, right? And X should be checked based on this one, fair resistance. Okay. Yeah, and for the beams, to design the fire resistance, this is the B for the T shape. Yeah. I shape. They have the same, and it's according to the boundary, right? Continuous beams. Yeah, for B, columns. Yeah, this one, here. Yeah, the cover and the minimum dimensions, they will related to these covers to have adequate fair resistance. Okay. This is an index about cover. What else is about the spacing of the reinforcement? Because some people students may have noticed that if the bottom we put 2 reinforcement, yeah, it's easy, right? Just like at these corners. But if here we have 4 or more steel bars, so this spacing S has a limit or not. Yes, during the code it pointed out, because for the spacing of the reinforcement will affect some things, so we give a suggest values for construct structure, yeah, to permit concrete to flow. Yeah, here I have to point it out that because if there's a dense reinforcement, means spacing is small. You know, the concrete is a liquid pour on the cage. They can't pass the steel bars cage, right, to reach to the bottom. So it needs have enough space for the aggregate to flow, yeah, for the concrete to flow through this one. What around during the construction, the clear distance between the bars should not be less than the maximum bar size. If the bar size we choose the 20, right, there the spacing should be larger than 20, right, than 20. Yeah, not it give you the concrete, the specific values. Also the maximum aggregate plus 5. Yeah, if the aggregate is 32, so the spacing should almost to the 40, right? This one is 37, but the spacing should be larger than these values. If the bars are separated into the different layers, each layer should be located vertically. That means not hinge the concrete pass through the cage to the bottoms. Yeah, for the boundaries can be adopted for vertical bars. For heavily reinforcement members, boundary can be used for 1, 2, 3, 4. Yes, do not more, because it's not good for the structures. What else is, for most cases, the thermal and shrinkage can be controlled by using the reinforcement area. So if the steel bars we use more, right, the bond stress is strong in the beam in the structure. That means it will hinge the structure has the shrinkage. So it's good for beam. Yeah. So consider the Dex effect. So the minimum reinforcement area, like the section area is B and the D, right? The total A equal to B multiply D, but the reinforcement we put here should have the minimum values. If it's smaller than this minimum values, means the shrinkage and thermal will totally affect the structure, will give the bad effect. Yes, for concrete in these levels, they will always give you the minimum values. And on cracking concrete, suddenly stress transfer from concrete should not yield at the steel. Yeah, these tables list the minimum area. This one is the minimum area should larger than these values, right? Larger than these values. Also, this one has the requirement for we to construct. If there's not enough about steel bars, some is construct steel bars. just only reset to satisfy about minimum reinforcement area. They do not bear the load, but we still set it in the B. Okay, this is a knowledge that for you to construct a beam or construct a structure that sometimes we see for a cage, right? Steel barred cage. They have the dense steel bars, but exactly what we calculate, only 4 steel bars is enough, right? Enough. That means this is the provide tension, and what else? Just to provide here to prevent shrinkage or the thermal effect. Yes, after that we realize the covers and the spacing of the steel bars. Now, in these sections, we will talk about the deflection. This is the important things, okay? Important things we need master. For the deflection, some people are ready to know, right? For structures mechanism, we always calculate for a frame, under the load, we calculate how many deflection, how much or the values of the deflection that we can calculate from the knowledge, right, to know. But here, we need to do this check about serviceability limit stage check about deflection. For the code, we know the formation of a member structure should be small enough, can't be large, because it will affect function or the appearance. To prevent appearance, the quasi-permanent load, okay? If you forget this limit state design, should go back chapter 2, okay? Chapter 2. There's a formula for you to calculate quasi-permanent load. Chapter 2. Of the structure under the quasi-permanent load, the deflection should be smaller than these values, okay? And look at here to prevent the damage of adjacent part of structures. They have a more strictly limit than these values. Okay. Look at this explanation there, except the dead load, because it's just the damage affect adjacent part, not on this part, this span, right? This span. Yeah. To calculate deflection is quite complicated due to cracking. So if you do not like the structure mechanism, because it had what we talked in reality, right? They had some crack. Of course, it will affect structure's deflection, right? How to get accurate the deflection? How to consider that? Yeah, it will be taught in this section. Yeah, look at here. The following factors will affect the deflection calculations. Yes, support regime, the different boundary quasi-permanent load. Yeah, always difficult to be estimate, right? May leave some errors. Although the crack happened on the beam or the structure member will affect the deflection. Also, floor's finish portion. For the floor, we do the design. In reality, they had the door and the floor. How to estimate the load? We should do some simply simplification, right? Simplification. Yeah. This is the two important X, importance, critical values. Critical values. And for the formula, how we to do the calculations. Okay, follow these formulas here for material mechanics. We obey this basic formula. Okay? Basic formula. 2 times constant C and the C2. This one, I think, you may learn from the structural mechanisms. Y is the deflections of the structures. Deflection function can obtain by double integrations of the moment function. For Y is the deflection. X is the place along the structure. We use the beam to explain. This is just X. Y is this directions, deflections. Vi is the stiffness, right? So look at here. This is the basic formula. We transfer at this one and use this these conditions. We can obtain these values. And what else is use the x equal to 0. This is the simply supported beam, right? For this formula. Now we get the y. The maximum deflection is depending on the square of a span. Square of a span and the curvatures. This is curvatures. And the squares of the spans have this form, right? This form. This form. Simply supported beam. For general beams, they have different boundary. Yeah, the form may be the same, but the coefficient is different. Okay, so people summarize the beams or the members, structure members under the different loads. They get the coefficient K, right? And they help us to get maximum deflection of the structure, right? If we get the maximum deflection, then we can compare it with the span multiplied 250 with 50, this index to compare it or satisfy or not, right? The problems will be solved. But it's enough or not? No. Look at here, because here, what's the equation we derived? Use the elastic theory, right? Elastic theory. But we have to know for concrete beam, due to the grip of concrete crack of a concrete or shrinkage of concrete, that may cause larger deflection. The elastic theory is not enough to do the deflection calculations. Here we have to use the plastic. Use this theory to consider the deflection to get more accurate deflection values to compare. So we need to use the plastic theory to do the deflection calculations. Okay, here we use creep effective modulus or equivalent modulus to consider the creep effect. Here's okay. Look at here. This is creep coefficient. We can check from these tables, and this one is the modulus of the concrete, and this is the time, and this is the atmosphere or the environment, humidity. So the different values we can choose, and substitute the values in that. We can consider the effective modulus. For this one, we considered creep effect, and another is a cracking effect. For concrete beam under the serviceability limit state, there are generally several flexure cracks will caused by bend moment. They just look at here. This is the beam. On the bottoms, they will have several crack. So in this part, of course, will affect structure's deflection, right? And in the elastic theory, we used these formulas depend on the square of the span and the curvatures. Now we use the average curvatures in the deflection design. For uncracked cross-section, the second moment uncracked, right, can calculate. This is the calculation. This is the expressions of this second moment of area. For cracked cross-sections, look at these figures, right? For this part, provide the compressions. This one is on the tensions, right? For the second moment area, we following these figures. This is the section, equivalent transfer. So use the first moment area to solve the x. Then substitute x into the here. For these values is what we obtain from the creep values at here, right? This is the materials modulus, because there is affected by crack. So this one, the curvature, we use the average curvature. It's related to the crack or the uncracked. For this one and this one, we use the different second moment of the area in there. And for coefficient, we need to consider tension stiffness at here. This is expressions, single short terms. Yes, for this parameters is the key will important to get these values. LCCS, the curvatures due to the shrinkage crack can both calculate. For this is one way, right? Another way is that we use this one. For X is the first moment area, about central section I the second. Curvature due to shrinkage can be calculated. Shrinkage, concrete. This is the concrete shrinkage. The curvatures we use the same way to equivalent to consider together to evaluate the structural members deflection. Yes, for the shrinkage. Okay, look at here. We need to check about these tables. Okay. So there's include three parts. One is the creep. We use the creep coefficient. Second is cracking. Cracking is we considered the eye uncracked or the cracked. And the third part is the shrinkage. Right? Shrinkage. We use the equivalent method. Use the curvatures. This one, and to calculate deflection. Shrinkage string, drying shrinkage and autogenous camping. Drying develops slowly, water loss spread, hardening of content. At early age. Okay, look at here. These examples illustrated here to show you how to get the deflection. So one is considered creep effect. The average modulus we note is this one, right? The nominal thickness of the beam. Look at this index, AC divided U. To look at here, the national size, 2 times AC divided U. U is the meaning, 2000, and AC is the area, right? Look at concrete area. Concrete areas, B multiply H, and U is equal to H, B, together is a 2000. Then get this one, and to check in the tables, we get the creep coefficient equal to this one. So the effective modulus, use the expressions, we get this one. And for consider the cracking, look at here for uncracked sections, right? Use the easily this one. So the curvatures, we substitute the values at here. Look at here, the M should be quasi-permanent moment. Get this one. This is be easy because uncracked belong to the elastic theory. And for cracking concrete at here, look at here. The FT-CTM, this one, 2.6. How to get these values? So go back to at here. To read at here, FCT, stress class. But for concrete belong to this one. Yeah, concrete strength belong to this one. And here, for these values, we get 2.8, right? This is the 210, and about 28. Yeah, this is the 201 and the 28. So these values. So substitute the values in this one. The expression values we can get at here is the 63.7, and for the C, we use these values at here, then get curvature, average curvatures. And for the epsilon, follow this formula. Now, and for the shrinkage effect, the same. For this values, how we can get is, look at here. For this one is 200, and for their inside, according to the so these values we get. Total curvatures, the deflections smaller than the limit, so it satisfies the serviceability limit state. So through these examples help you to know the deflection check. Okay, students, to read examples. Today's class is over. Thank you.